Well, this leads us to what I call the ubiquitous bathtub analogy. The bathtub you can think about as the amount, right? The amount of something. So it doesn't have to be limited to water filling up a tub, but in this case, you can think about the water level as population level. How big is the population size? The inflow, which you can think about as the water coming into the tub, could be things like births, immigration. You might have multiple sources that feed water into your tub that make your population level rise. On the outflow or the drain, these are any things that will affect your population in a negative way. So culling, starvation, weather, disease, old age, accidents. Culling is like, could be, if you're talking about fish, it could be fishing. If you're talking about elk, it could be hunting. Culling is the process of removing creatures from the population. Okay. Let's take a look at a couple more examples here of modeling. Let's say that we let y represent the number of elk in a particular region of Flagstaff t years after a study begins. So our variables are defined for us. Suppose it is known that 13% of elk successfully give birth each year. Complete the following differential equation modeling this scenario. So dy dt is going to be measured, first of all, in elk per year. How do we know that? Well, y is measured in the number of elk. T is measured in years, therefore our rate of change model will be elk per year. So the question we have to ask ourselves is, how many new elk do we expect to have each year? Well, it's going to be 13% of the elk currently there are going to give birth, right? So if, for example, there were 100 elk, then we would expect 13 new elk over the course of that 1 year. That is, at that moment, we would expect the population to be growing by 13 elk per year. Now we know that not all births are successful. We know that there are all these other things that are coming into play. But we're not going to take those into account right now because we're building a model simply based upon this one assumption that the population is growing by 13% per year. We don't need to become the scientists. The scientists are the scientists. They tell us what the model assumptions are, and we build those in. Okay, so if there were 200 elk, well, 13% of the 200 are going to give birth, so that means there are going to be 26 new elk in that, or the population will be increasing at that rate. At 300 elk, same kind of process. 13% of the 300 are expected to give birth. That's 39 elk per year. And you're probably seeing the pattern. Here, we're just taking 13% of the 100. Here, we're taking 13% of the 200. Here, we're taking 13% of the 300. And in general, I like to do this in general thing. If there were y elk, because y is the variable that tells us how many elk there are, then I would have 13.13 y elk per year as an instantaneous rate of change. So it's always 13% of whatever our population size is. And that is the reason why our differential equation is now, for the first time ever, well, maybe you've seen these types of equations in your career in your education, but this is a differential equation that is a function of the dependent variable, also known as an autonomous ODE. Pretty cool. We don't know how to solve this because it involves the dependent variable in it. And we'll soon learn a technique that's actually pretty simple in concept that's called separation of variables that will help us solve this equation. But we'll come back to that later. That's not the purpose of this video. Let's look at a more complex modeling situation. How do we realistically model? How do they know that it's 13%? So suppose a population of elk in Flagstaff is to be modeled over time in years. We would like to know the number of elk in the population at any given time. The following information is available. And I think I took this from Wikipedia for the gestation period of a female elk. Female elk have a short estrus cycle of only a day or two, and matings usually involve a dozen or more attempts. Okay, we're not going to take that into account because how do I deal with that? By the autumn of their second year, females can produce one and very rarely two offspring, although reproduction is most common when cows, that's I think the name for the female elk, weigh at least 200 kilograms. The gestation period is 240 to 262 days, and the offspring weigh between 15 and 16 kilograms. So there's lots of information here, but ultimately all I want to know is, okay, well, how many new elk are going to be born? So what is dy dt going to be? Same units as before, elk per year. So what's going to affect them? Well, obviously the weight will, right? The mass of them. Are they of the proper mass? This estrus cycle of only a day or two, I mean, that's negligible. That's really small in terms of years. So 1/365th is probably not going to have a huge impact. So I'm going to go ahead and ignore that for now. Dozen or more attempts at mating. I don't know how many times they mate. This doesn't give me enough information to go off. All I do know is that if I did have Y elk, if I had Y elk, well, first of all, Y elk doesn't allow me to determine how many new offspring are going to be born because some of those are male, some of those are female. So I'm going to make an assumption, assume 50-50 female-male split. Okay, so that means of the Y elk, 50% of them are female. These are female elk. And we're going to make the assumption that every female elk is going to successfully give birth because I don't know how else to do it without taking into account other information that I'm not given here. Now, I have to figure out, it's not the case that if I had 100 elk that there would be 50 new births, right? That every single female would give birth to one calf per year because it actually takes less time. It takes less time than a full year. So this is the female elk, but keep in mind that my units need to be in elk per year. So this actually tells me the number of elk, but not with respect to time. So in order to get elk per year, I have to divide this by how long it takes to produce those elk. Well, it takes 240 to 262 days. So I'm going to make another assumption here. And again, I wouldn't expect you to be able to do this right off the bat, but as just a modeler, how do you approach these problems? We're going to assume, or I'm going to assume, that halfway between this, that it will take 251 days to give birth. Now, I'm not an ecologist. I don't know how this works exactly, but I'm going to make this assumption that every 251 days a new calf will be born from every single female. And again, not a good assumption, but it's the best that I have to go off of. Now, I can't use days, I need years, so 251 days is 251 365ths of a year, assuming there are 365 days a year. So if I divide this by 251 365ths, that's in years. This here is in elk, and I now have elk per year, which if we do the division of 0.5 divided by 251 365ths, we get about 0.34 from that. So this component here is going to tell me that I get 0.34 Y. Now you can see that that's less than 50% because 50% of the population is female, but and my mistake, this is not 0.34, this is actually 0.73. Because I multiplied 0.5 by 251 over 365. And so this makes sense because if you think about it, even though 50% of the population is female, it doesn't take a full year for each female elk to give birth, and we assume that every 251 days, every female on average is producing one elk. And so that means that over the course of a year, we expect that to be a little bit bigger than that 0.5. So my model for this equation, after all is said and done, would be 0.73y. So with other types of models, where we're not modeling population, we take a very similar approach. This last example is a non-population model, because of course we're not always modeling populations, but it's a famous one. It's called Newton's law of cooling. And Isaac Newton, among others, observed that the rate at which something cools or heats up is negatively proportional to the difference between the temperature of the object that is getting cooled or heated, T, and the ambient temperature, T naught. So let me draw you a little picture of what we've got going on here. We have some sort of object, let's say a cup of coffee. So here's our cup of coffee, and there is our little handle. And so we have this hot coffee, right? And we put it inside of a room, right? We put it inside of this room, and inside of this room you have your thermostat. And of course, there's going to be some temperature of this room. Maybe that room is 78 degrees Fahrenheit. So not a bad temperature for a room during the summer. And this coffee cup, or the coffee inside that cup, has a temperature that of course changes with respect to time, right? So little t is time, capital T is the temperature, and the temperature of that cup of coffee just depends on the time, right? So this guy is going to be cooling off, especially if it's piping hot at 160 degrees Fahrenheit. So we might actually say that the temperature at time 0 is 165 degrees Fahrenheit, for instance. But what we really want is we want to model the rate at which the temperature changes per unit of time. So let's read this and translate this carefully. It says, the rate at which something cools or heats up is negatively proportional. Okay, so when we see negatively proportional, what that means is that, first of all, it's negatively proportional. Well, there's going to be some proportionality constant. And proportional to means it is multiplied by that constant. And so it's negatively proportional to something, right? Negatively proportional to the difference between the temperature of the object and the ambient temperature, T naught. So the difference between them is T minus T naught. And it has to be done in that order, because look what happens. So K itself, K is the proportionality constant, and these constants are always going to be greater or equal to, I shouldn't say equal to 0, that wouldn't make much sense, but is always greater than 0, right? So the constant itself could be like an R rating for insulation of a house that tells you basically how much insulation capability does that, insulative capabilities does that insulation have. And the reason it needs to be T minus T naught and not T naught minus T is, let's think about this for a second. So if I have 165 degree coffee minus a 78 degree temperature, this is going to be a positive number right here. Now, what I have here is this is going to be a negative number, right? Because it's going to be the negative of a positive constant. And when I multiply those together, I am going to have a negative times a positive, which is negative. So that tells me that the rate at which the coffee mug is changing is the temperature change is negative, which means the cup is cooling off. If, however, you switch these around and you wrote T naught minus T, now let's think about this. So the temperature of the room is 78, temperature of the cup of coffee is 165. That quantity right there is negative, right? This is going to be negative. This quantity right here is going to be negative, and when you multiply a negative by a negative, you get a positive, and this suggests that the coffee is heating up. And I'm going to put a big question mark and exclamation there, because clearly this situation doesn't make sense. How could a hot cup of coffee start heating up in a room that is cooler than the cup of coffee? So sometimes these little details make a big difference in our modeling approach. We'll go ahead and stop there with this video, and we'll get more into how we begin solving equations like this. In fact, this one here is also autonomous, just like the rate of change model above.